When we started talking about mechanics, I mentioned there were three approaches we were going to learn this semester. The first was Newton's laws, which we just finished. The next was work and energy, that will start here. And after this will come momentum. I also mentioned that work and energy and momentum were sort of repackagings of Newton's laws. There's nothing fundamentally new in this topic of work and energy or in momentum that will come later. But the advantage they do bring is essentially a more sophisticated, targeted, precise approach to the subject. Newton's laws are a very fundamental tool. If you have an object and you want to know what its motion is, the recipe using Newton's laws is very clear. You draw a free body diagram, you add up all the forces, and you solve for whatever unknown you are looking for. It could be the acceleration or the magnitude of some force. Whatever it is, the recipe is very clear. It's a very straightforward mechanical approach. Draw the free body diagram, sum the forces, do those steps every time. Work and energy that we'll start talking about now is a much more refined approach. Over the 20 years or so that I've been teaching this course, I've come to really appreciate the importance and the power in the idea behind what I'm about to tell you. And I want to try to convey to you in this talk how cool this approach is, how it's fundamentally the same, but how in practice it's so different that it allows us to tackle a whole range of problems either more easily than we could with Newton's laws, or in some cases, tackle problems that are really intractable with Newton's laws altogether. So this tool of work and energy really opens up for us a whole new way to tackle mechanics problems, and it gives us, in almost every case, much more insight and a much more refined look at what's going on. This is a really nice topic, and in this first talk on it, I want to try to lay out for you the big idea behind it, and then as we work through it here, I'm going to end up by showing you one of the most important equations in this topic. It's called the Work-Kinetic Energy Theorem. Alright, so let's start by taking a look at the basic idea behind this thing called work and kinetic energy. Suppose we have an object that's going to move along some curved path. And here's our object. It's at the beginning, at the initial point, and this is a box or whatever it is. It doesn't matter, right? Now, this thing is going to move along this curved path because various forces are acting on it. The forces are going to push it forwards and then make it turn so that it stays on this path. There could be many forces acting on it. Let's consider just one to begin with. Maybe this is a box and we're going to push on it. So we're going to push on it with a force that I'll call F1. If this force has a component in the direction of the box's motion, like I've shown it here, then as we walk along, if this force keeps pushing in the direction that the box is moving, so now the force is going to push this way, and this way, and this way, and this way, our intuition tells us that this force pushing in the direction that the box is moving is going to tend to speed the box up. It's going to tend to make it move faster. If, on the other hand, there was another force that was acting, maybe it's friction, that's acting against the box's motion, so it's here, and then it's over here, and then this way, and this way, and this way. If that force is opposite the box's motion, our intuition tells us that it's going to tend to slow the box down. The thing we're looking at here is the component of the force not necessarily along the x or y direction, but along the direction of the velocity vector, in the direction of the path, or against it. That's an important difference from what we did with Newton's laws. Let's think now about the component of the force in the direction of motion. If you're pushing on something in the direction it's moving, you tend to speed it up. If you push on something opposite the direction it's moving, you tend to slow it down. Maybe there's another force that would push sideways on this thing, this way. Your intuition in this case might tell you that that force could make the object turn, but it won't change the object's speed. The big idea here, the underlying consideration, is whether a force has a component in the direction of motion, tending to speed the object up, against the direction of motion, tending to slow it down, or perpendicular, not changing the speed at all. So there should be this relation between the component of force in the direction of motion and what happens to the object's speed. That takes us to the definition of work. In physics, when we talk about work, this is what we mean. We mean the line integral of the force along the path. In physics, work is done on an object by a force as the object moves along some path. Let's talk about this ds element and what this line integral is telling us. I'm going to erase some of these force vectors so we clean this figure up a bit. This vector ds is a line element of the object's path. It looks like this. If the object's moving this way, ds would be a tiny step in that direction. This way, ds would look like this. ds is everywhere parallel to the path. And as you move along in the direction of ds, you trace out the object's path. Remember from our talk on the dot product last time, the job of the dot product is to pick out the component of one vector in the direction of another vector. And that's exactly what's going on here. There's a dot product between the force and the path ds. So this dot product is picking out the component of the force in the direction of the path. And this is important because, as we just talked about, that's the component that's going to tend to speed up or slow down the object. And this integral tells us to add up those contributions all along the path. So what we have here in our definition for work is something that's telling us to add up the component of a force that's tending to speed an object up or slow it down as it moves along some path. Really nifty definition. It's telling us to pick out the component of some force speeding up or slowing down and to add up that effect over the object's whole path. That's what this definition is telling us to do. Now there might be more than one force acting. Before we had friction and we had some other force on here, and each force individually tends to speed up or slow down the object. And what we're really interested in is the net effect. I'm very often interested in not the work done by one single force, but the work done by all forces acting on an object, because that's going to tell me in the end whether the object has finally sped up or slowed down or not changed speeds at all. So very often what I want is the work done by what I'll call all forces. And what that means is to add up the works from every individual force. So we're going to sum over all of the individual works I. There might be three of them. There might be this force F1, there might be friction, and that other one. So I would have three terms in this sum. That'll give me the net effect, and in the end, tell me whether the object sped up or slowed down or whatever. So let's write this. The work done by all forces is the sum over all of them of the work done by the individual forces. Here's the ith force. We find its component in the direction of motion and add it up over the whole path. That's the idea that this whole chapter is based on. To pick out the component of the force in the direction of motion, that will tell us whether that force is tending to speed up or slow down the object, and then to account for all of the forces that are acting, so that what we end up with in the end is a way to figure out the net effect of all of this, whether an object changes its speed or not. That's the big idea that underlies this chapter. What I want to do next is write down for you and then show you how we obtain the so-called Work-Kinetic Energy theorem, one of the most important equations we'll have in this chapter, although as we go through it, we're going to rewrite this equation in more user-friendly ways. Okay, so here's the equation that we're going to obtain next. What we're going to find when we do this integral on the right-hand side here is that the work done by all forces acting on something tells us the change in what we'll call kinetic energy, where K, this kinetic energy, is going to equal half mv squared. And this is where we see the change in this object's speed. Half times mass times its speed squared. So again, if we interpret this equation, it tells me add up the work done by all forces acting on an object. Remember, the work is this thing that tells us how each force individually tends to change the object's speed. Add all of those up, and it'll tell us the change in this thing, kinetic energy, that has to do with mass moving at some speed. So if the speed changes, it's going to change the kinetic energy of our object. This equation is called the Work-Kinetic Energy equation. I'll abbreviate it this way. It's an important one. If there's no work done on an object, no net work, there'll be no change in the object's kinetic energy, and therefore no change in its speed. If positive work is done on an object, the change in the kinetic energy will be positive, and the object's speed will go up. If negative work is done on the object, its change in kinetic energy will be negative, and the speed will go down. All right, let me show you the derivation of where this equation comes from. I know derivations don't always provide the fondest memories to students in physics classes, but this one I think is worth seeing. So if you have any interest in this kind of thing, check out what I'm going to do here. If you don't, you can skip it, and next time we'll talk more about this equation. But if you want to see where it comes from and how we obtained it, stick around. I'll show you that next. So what I'm going to do is move this stuff up to the top so that we have some room to work. I'm going to shrink it and move it up here. That's the result that we're after, the Work-Kinetic Energy theorem. The rest of this I'm going to get rid of, except for this over here, which is going to be our starting point. So let me move it up here, and we'll start our derivation from there. The first thing I want to do is to move this summation sign inside the integral. I'm trying to evaluate the work done by all forces acting on the object. And so far what I have is something that tells me to add up all of the individual works. The first interesting step comes from bringing that summation inside. This now tells me not to add up all of the individual works, but to add up the net work. To add up the work done by the net force. So it tells me now to add up all of the forces. Let me redraw this path up here. So take the object that's going to be moving along the path, find the net force on it, and find the work done by the net force. Notice the similarity and difference between this and this. It's interesting. This tells me to find the net work. This tells me to find the work done by the net force. It's interesting that those are equal. Now, we know that the sum of the forces on something equals mass times acceleration. So now, if I replace that, I have mass times acceleration dotted into this element of the path. I'm going to replace that with the definition of dot product that we came up with in the last talk. Remember, we said if you know the components of two vectors, the way you can calculate the dot product is to multiply the x components and add it to the y components multiplied. If you're in 3 dimensions, you would add it to the z components multiplied also. Here, we can rewrite this as ax times the x component of this plus ay times the y component of this. And if we're in 3 dimensions, plus az times the z component of this. Now, what are the components of this ds vector? Let me draw this again. Here's our path, and I'm going to draw the ds vector big this time so that we can see it. The x component of a step along the path, I'll draw it in green, is this. It's just dx. The y component is how far we moved in the y direction, and that's just dy. So the components of the ds vector are just dx with an I hat to tell us we went sideways, and dy with a j hat to tell us that we went vertically. So when we do this dot product, what we end up with is mass times ax dx plus ay dy. I'm going to write it in 2 dimensions. And now I have to integrate this all along the path. So I'm going to integrate from my initial x and y locations to my final x and y locations. So that's the integral I need to do. The next step comes from using the chain rule. Let me write out what we're going to do, then we'll substitute it in and clear out some space. If I apply the chain rule to the definition of acceleration, ax, I can write it as dvx dt, which is the definition, or using the chain rule, dvx dx dx dt. Now this is the velocity. It's the x component of the velocity. And then I have a dx down here. Now look at what's going to happen when I substitute this into the acceleration up here. Ax dx is going to become dvx dx vx from what we just did times this dx right here. So this one's right here. These in effect cancel so that ax dx can be rewritten as vx dvx. We have changed the integration variable. Whereas we used to integrate over the path, the positions, now we're going to integrate over the velocity components at points along the path. Let's write it out and we'll see this. So after those substitutions and simplifications, we have this. The integral of mass, vx dvx plus vy dvy. And I'm going to erase this stuff. Okay, now what am I integrating over here? I used to be integrating over the positions, but now I have to integrate over the velocity components at those positions. So I'm going to integrate over the initial x component of velocity and y component of velocity, and I'm going to integrate all the way until the final. Okay, so find the initial x component of velocity here and y component. Every step along the way, take those velocity components, integrating all the way until we have the velocity components at the end. These integrals are easy to do. It's just the integral of something d something plus something d something. And that's going to give us half the something squared. So we end up with half m vx squared plus vy squared evaluated at our limits. Vx initial, vy initial to the final. Before we rewrite this again, let's notice that this is just the square of the object's speed. From the Pythagorean theorem, this is just v squared. So I can replace this with v initial and this with v final. So what we have is half m v final squared minus half m v initial squared. Something final minus something initial. That's the change in that something. This whole thing apparently works out to the change in half m v squared. And that half mv squared is what we're going to call kinetic energy. It's a kind of energy that's associated with mass that's moving. So we can say, in the end, after all of this, that the work done by all forces is the change in this new thing we're going to call kinetic energy, where kinetic energy is half mv squared. It's energy associated with mass that's moving. But the important thing here is that if you account for the work done by all forces on an object, it tells you how the speed of that object changes. That's our work-kinetic energy theorem that I have a smaller version of up here. We'll come back to this equation and get some practice using it and interpreting it and getting some practice with it. But I wanted to show you here where it comes from and try to describe for you the big idea behind this chapter. In the next talk, we'll get some practice calculating works done by forces on objects as they're moving.